Welcome back. Today we are talking about cellular transport and specifically passive transport. And so I want to start and begin by reminding you that the plasma membrane is built of these phospholipid bilayers with embedded and associated proteins, lipids, and sugars, right, on the surface. Now we say that plasma membranes are selectively permeable. This means that they select in part what gets to enter and leave unassisted. You can imagine that the phospholipids are next to one another, right? Like kind of like my fingers, but certain things can actually fit through those phospholipid heads. Some small molecules can enter and leave then unassisted, right? They can enter those spaces and come into the cell and out of the cell as they wish. Now, showing this diagram over here, you can see that there's gaps in our membrane if the membrane is in yellow, and we put a dye, a red dye, on one side, then naturally things will want to move from where they are highest in concentration, right, on this side, to where they are in lowest concentration. So the dye is going to move over time from high to low concentration until it reaches something called equilibrium, where you have equal amounts of dye on either side of that membrane. Now we say that membranes are selectively permeable because some things can sort of just move into equilibrium unassisted. But certain things, large particles you can imagine, won't fit, right? And so they cannot go into the cell or out of the cell unassisted. Or if you think about the chemistry of our cell membrane, much of the centerpiece is a nonpolar fatty acid set of tails, right, that are sandwiched in there. And so a lot of things that are either polar or charged, things that are hydrophilic or water-loving are not going to be able to enter and go through that nonpolar area. And so this makes it very difficult for certain particles. This is because size matters when it comes to being able to transport in and out of the cell, and chemistry matters in order to sort of get through that sort of nonpolar section of the cell membrane. So we say that plasma membranes are selectively permeable. However, today I'm going to talk about this kind of transport, passive transport. This is a kind of transport where energy is not required in order to make this kind of transport happen. In active transport, we will talk about that in the next part of our cellular transport lectures. And this is where we have things entering and leaving, but we're going to have to actually provide energy to make those kinds of movements happen. Now, passive transport and active transport, if we look at them, passive transport requires no energy because it is moving things with their concentration gradient or with what nature wants to happen, from areas of high concentration of chemicals to areas of lower concentrations of chemicals. That's what normally particles want to do in nature. A good analogy for this is imagine a big hill and you're riding a bicycle, right? From higher levels to lower levels. If you're just riding down that hill and you are going with gravitational forces, right? So you're following the laws of gravity to pull you towards the center of the earth, then you don't have to pedal your bike. You can just glide down the hill for free because you are following those laws of gravity. If you are following what we want to see or what happens naturally to these concentration gradients where they're moving from high areas to low areas, then you don't have to pedal. You don't have to provide energy in order to make them happen. If, on the other hand, you want to go up the hill, right? You want to go from where it's low and then ride your bike up to sort of a higher elevation, then this goes against gravity, right? And this is what happens in active transport. We're moving chemicals against their concentration gradient. We're moving them from areas of low concentration to high concentration. When we go against what wants to happen naturally, then this requires energy. Just like you would have to pedal that bicycle and put energy into your bike to get up onto that hill, the same thing is going to happen in active transport. Today we're going to focus on passive transport in part 1, and then we will look at active transport in part 2 at a later time. So passive transport, there are 3 kinds: simple diffusion that I want to talk about, facilitated diffusion, and osmosis. So I want to walk you through how these kinds work, but remember, All three kinds are going to be moving things from high to low. All three kinds will not require energy in order to make this movement or this transport possible. So the first kind is simple diffusion. Simple diffusion is where particles, so these are the solutes, things dissolved in water, are moving from high to low concentration through a membrane without any assistance. So they're going unassisted. This typically these are chemicals that are either very small, they're non-polar, right? The correct chemistry so they can cross very easily. If they're moving from high to low until equilibrium is reached, then no energy is required. And you can see this is a group of dyes. If you put all red dye on one side, all purple dye, then over time they will move from areas to high to low concentration until they reach equilibrium. A good example of something that does this in your cells is oxygen. Oxygen is very small, and in some cases it can move from high to low straight across cellular surfaces and then enter new cells. And so oxygen might be a good example. Keep in mind those small particles. Facilitated diffusion, on the other hand, is a kind of diffusion where you're still moving something high to low. You are still not requiring energy, but this time the particle is too big to move unassisted. And so the facilitated part of this diffusion is a transport protein. We can have these transport proteins inside of our membranes. They can be channels like this, or sometimes these carriers are kind of like rockers, or imagine saloon doors, right? In the old Western movies. These kinds of gates then have openings that allow things to come from high to low concentration and either rock into a cell, out of a cell, or these channels allow this facilitated diffusion. Again, it's facilitated because it requires a transport protein to provide a way for larger things, for polar molecules, charged molecules to move from high to low into and out of the cell. So this will be a lot of like salts and charged particles and things like that might move in this way. The last kind of passive transport is osmosis. This is by far the most complicated kind. This is diffusion of water. So I have that like in bold in your notes. The first two are moving particles. So the solutes are moving in both simple diffusion and facilitated diffusion. But in osmosis, this is the diffusion of water. It's a special case where water gets to move from high to low concentration due to solute concentrations around them. And so there are cases, over here in this tube, I show a membrane across the surface. There are cases where the membrane, the holes in the membrane, or the places where things can sort of move through, are too small to allow certain kinds of solutes, but water can move freely. And in these cases where almost like solutes get stuck, right, on one side or the other, then water will move until the ratio of water to solutes is equal. So you can see we start out with even amounts of water, but the solutes are much higher. So water is going to move towards those like sort of high solutes or salts, and then until an equilibrium between the amount or ratio of water to solutes is equal on each side of the membrane. There are three kinds of solutions that cells often find themselves in: isotonic solutions, hypertonic solutions, and hypotonic solutions. These are all cases of osmosis where water's moving because of these solute concentrations in and around the cell. So let's work through these three solutions. Isotonic solutions, this is where you have equal concentrations of solutes, both inside and outside of the water, equal concentrations of water inside and outside. So we say that there's no net movement of water. For animal cells, this is their favorite kind of solution to be in. We typically want to be in an isotonic where outside and inside surfaces are sort of matched. For plants, this is where they just begin to wilt. And so plants don't prefer, they have like another solution that they often prefer over this one. I remember isotonic solutions as an iso means isosceles triangle, and an isosceles triangle, where you have two sides the same. So in cells, this is where you have equal solute and water on both sides of your membrane in an isotonic solution. In a hypertonic solution, you are going to have more water inside the cell and less solutes. That means you have more solutes outside of the cell and less water. Solutes get stuck, and water gets to move from where it's highest inside the cell to out of the cell. This causes the cell to shrink and become dehydrated. So cellular dehydration is caused in a hypertonic solution. And water is going to sort of move towards your salty areas. So this is when cells get a very salty environment around them, or a lot of solutes, a very sugary environment, or something like that in the water around a cell. It would cause the water to sort of exit. In animals, because this is dehydration, this causes our cells to shrivel up. You can see the cell is kind of collapsing in this picture. We call this crenation. And in plants, it also causes the plasma membrane to pull away from the cell wall and sort of collapse or dehydrate. The water exits, and then the plasma membrane kind of shrivels up. This is called plasmolysis in plant cells. Neither cell likes a dehydration situation, and so neither plants nor animals prefer this particular kind of solution. I remember this as when you're hyper and whatever, you sweat a lot and you're losing water, and so cells in a hypertonic solution will lose water, or water will exit the cell. The last kind of solution is a hypotonic solution, and this is just the opposite of what we saw in the hypertonic solution. In a hypotonic solution, you have a lot of water and less solutes on the outside of the cell, less water inside the cell, more solutes, and so water wants to move from where it's highest outside the cell to inside the cell where there is less water. Water then moves into the cell, and the cell swells up due to this excess water. In animal cells, this can actually cause our cells to burst because that plasma membrane is so fragile, it can burst. It's almost like having a balloon that you fill with too much air. It can eventually pop. Right? In a plant cell, though, they have this external cell wall to protect them from lysis. And so in plant cells, it's almost like you have a balloon in a cardboard box. The balloon you would fill up all the way to that like sort of box edge, right? And then that cell wall or that box edge would hold that balloon and keep it pressurized. We call this turgid, and keep it from popping. And so for plants who need a lot of water in order to carry out photosynthesis, this is their favorite situation. Turgid sort of cells often means that stems, herbaceous stems or green stems, are standing up straight, and they have pressure to like sort of hold their stems up straight. When I learned this, I remembered hypo sounded like hippos, and hippos are fat, right? And your cells get fat with water in this particular situation. So these are the kinds of passive transports that I want to talk about: simple diffusion, facilitated diffusion, and osmosis. All three kinds of passive transports move things from high to low concentration, and no energy is required. Next time, we will look at active transport.